first presentation of the day is going to be What's New in PowerLog from Fred Jensen. Fred Jensen is the product manager for PowerLog here at Software. Fred is based in Houston, Texas, and he has over 41 years of experience in roles including wireline field engineer, sales engineer, petrophysical consultant, and software development management. He's worked on many field studies in most of the major basins around the world and has extensive experience with integrated interpretation techniques. So without further ado, I will hand over the screen to Fred.
Thank you, Monica. I appreciate the introduction. In reality, all those years of experience merely mean that I'm old, but I guess that's okay too. It beats the alternative. All right, we're going to discuss a few of the new features in PowerLog. We're not going to discuss all of them because we're constantly adding new features and functionality to PowerLog, specifically based on what's requested by our client base. So the purpose of this meeting is to get feedback from our customer base and to let us know where we can improve. We're constantly modifying PowerLog, and almost 90% of what we do is based on what our clients recommend or request. So please, the main goal of this meeting is to get input from y'all. And I'm going to discuss some of the new features in PowerLog. Certainly not all of them by any means, but just some of the highlights. So here's the agenda. We're going to go through a quick history of PowerLog. I'm doing that in case anybody present isn't aware of the history of PowerLog. And then we're going to go into some automated log editing, which we've really been focusing on because we had a lot of input that said that's something people are interested in. We're going to look at outlier detection, automated curve patching, and similarity analysis. And then we're going to look at a new functionality that we don't think we've given enough attention to, and that's Facies-driven zone attribute calculator. And so we're going to show how you can create the zone attributes from a Facies curve and then automatically generate a block curve from the results. And then we're going to take a look at how you can now use Python extensions in PowerBatch and Workflow Manager. And that was requested by one of our clients. And I will say one of our larger clients, and I'm going to try to get my pointer to be a laser pointer. I think that's cool. That they really wanted the ability to build their own Python extensions and put them in PowerBatch and Workflow Manager. So here's PowerLog, and the highlights are very easy to use. It's multi-user, multi-interpreter. We're on a commercial database. We've got lots of ways to handle data, to do computations, to manipulate the data and display it. It's rich functionality. It's been around for a very long time. A lot of advanced modules. We've had 2D user programming a while. Python extensions was added a few years ago. We also have a cross-section correlation module now. That's just a few years old, and a strat column so that you can build your strat columns for the purposes of creating zones or for displays. So here's some historical perspective. PowerLog was first released in 1983. So I guess we're going to have our 40-year anniversary next year. It was the first Windows-based interpretation. It was purchased from Petcom by Landmark Graphics in 1991. And the strange coincidence, I worked for Landmark Graphics in 1991 and worked on the conversion of Petcom to the Landmark Graphics Petrophysical package, which I dissociate myself from then on. And then we have a PC version of PowerLog was resold to Petcom because Landmark Graphics didn't do a great job of it. We purchased it back from Fugro Jason in 2005. We rewrote it. I joined right after it was finished in about 2010, and then it was purchased by CGG in 2019, and most recently by Constellation Software in 2021. So let's look at automated log editing. This is outlier detection, and Outlier detection is something we've all done as petrophysicists, but this kind of formalizes it, and it does one extra thing that's really important. So we're taking a group of wells, and we want to see where is our outliers? Where's the data that's not so reliable? And in this case, because it was available, we're going to use the caliper and the delta row curve to look for the bad data. And we're going to define the level of impurities, what percentage of bad data do we want, and then we're going to smooth the outliers, and there's reasons for that, and we can go into them if you need to. We're going to create the outlier flag, an outlier score on how big an outlier is it, a smooth outlier curve, and the reference curve OD null. And this is very important because not only do we detect outliers, we create a curve where the depth curve does not exist where there's an outlier. You say that again, it removes the depth curve where there's an outlier. And I'll show you why that's important in a few minutes. And so we run it on all the wells, and here you can see your outliers in red. And on the log plot, you can see where you have your outliers, and you can see we have a lot of washouts. And this is a pretty typical in a lot of areas. This is a Cotton Valley well. And the outliers, and you can see on the delta row curve where you have it, and they're in the shale sections. The shales are washing out, and we've got to find a way to get some better log responses in the shales. So this is the outlier detection module. It's great. It can be used to detect all kinds of outliers and has a lot of other uses than this. Now we're going to go generate a synthetic curve over that same area using the same group of model wells. And notice the sampling grid is the same as OD null. So we aren't using any of the outlier data in the generation of the synthetic curve. That is so important. Now, I mentioned here we also generated synthetics with this, which is multilinear regression. We also did a TensorFlow, a random forest, and a gradient boost 200, which is a gradient boost. And all of these, by the way, use the sampling grid of same as null, and none of the outlier data were included in the generation of the synthetic curve. That really improves the quality of your synthetic curve. And then once we have a synthetic curve, we have this log edit patch, and you can bring in all your curves, and you can say, I want to take my original curve, and I want to put an outlier. And here we use the smooth outlier detection because we want to eliminate any edge effects. So we want to extend the outlier a little bit above and below so we remove any edge effects. And then we're going to splice in the synthetic and generate a merge curve. And we're going to splice in the synthetic wherever we have outliers. So here you can see the green curve is the original density. The blue curve is the synthetic, and the red curve is the merged. And the red curve will be our final curve. And you can see through this area where you had really bad data, you've now got really good high quality data. This is the high quality synthetic. And you now have a curve which you can use for a lot of computations. This is a really nice way of creating high quality curves in bulk very quickly. We have another new tool called Similarity Analysis, and this one's a little bit more esoteric. So what is similarity analysis? So if you have a couple of wells with two curves of interest, your neutron and your density, different number of points in each well, how can you tell how similar the joint probability density functions are? How similar are these wells? So we run this process called similarity analysis, and it assigns a metric to the similarity of the joint probability density functions. And it extends this solution from 2 curves to n dimension in many wells. So as many curves as you want and as many wells as you want. And you can also do a plot, a heat map plot, and you can show the wells and how they overlay. And these are two very dissimilar curves, and they just don't agree at all. Here's an example run on a group of wells. And you'd say that all of these wells are pretty darn similar, except the Muzza well here, which is very unsimilar. And you might want to go look at the Muzza well and find out why it is so dissimilar. Here again, this is the Cotton Valley project. And while this one is the most dissimilar, these wells are all very similar, and they have excellent overlap. So I would think all of these wells can be grouped together without any concerns. They're all very similar wells with a very high Jacquard similarity. That's a nice group of consistent well responses. So what do you do with similarity analysis? Well, you can select your reference wells for your curve normalization. You can group your wells for generating a higher quality synthetics. We have a feature that allows you to just create well groups so that you can have groups of similar wells. It's really interesting to compare the similarities of your edited data to the similarities of your raw data. If it changes dramatically, I suspect you did something wrong in the editing process. You can group wells for complex interpretations. If a multi-mineral deterministic model applies to a well, it'll probably apply to all the similar wells. It makes it easier to do analysis on large groups of wells, and it can find anomalous curve data, and it can identify wells that do not belong. Sometimes wells are just not where they're supposed to be, and it's important to figure that out. And I'm going to show a real quick slide here, which is Facies classification. And we're going to just generate a Facies curve on one of the Cotton Valley wells. And we're going to use a Jupyter workflow. We're going to use agglomerative clustering, and we're going to put in just 3 curves. What we're trying to do is separate the shales from the sand. So we're trying to get a 2 facies, and we just want sand shales, because we're going to go ahead and use this to create block curves. And then we're going to generate an output curve, and then we'll use random forest for supervised facies. We like supervised facies because you can get probability curves for the probability of the facies, and you can handle a large number of wells. Unsupervised clustering, you're limited to how many wells you can show. In supervised clustering, you can process thousands of wells with no trouble. So here's the Facies zone attribute calculator. What you do is you go in and you run ZAC, and ZAC is a zone attribute calculator. And you can define these zones by hand in the ZAC, or you can define zones using a categorical curve. Tell it to use the RF20, the supervised facies, and it'll go in and it'll divide your curves up by facies. Now, you may wonder, why would I want to do that? Well, there's a lot of reasons you might want to do that. You might want to compute the means of all these curves in these intervals for input into a frac simulator. In fact, that was the original purpose of ZAC, was for designing for dividing wells up into zones for fracture simulation and developing the parameters to be input. In this case, we're just going to use it to develop the block curves, and we can automatically create the block curves based on the mean, the minimum, or the maximum. And this is a very quick and effective way of generating block curves. So here's your final block curve. to be used in reservoir simulation and quantitative interpretation for doing further geophysical studies. You just create the ZAC curves, you give it the names you want, and you run it, and boom, you've now created block curves to represent the data for over the entire well interval. A really nice, slick, easy to use feature. And the last thing we'll cover is extensions in PowerBatch and Workflow Manager. So what is an extension? An extension is a customized viewer processor that you write in a Python interpreter, like in this case we're showing Spider, and you create a module that plugs into PowerLog. And this is a demonstration of a processor, and it's designed to calculate the elastic properties, the Poisson's ratio and Young's modulus. So we write our little extension, and it has read-write access to the database, and it runs just like a PowerLog module. And I have clients who built hundreds of these things. They're very popular and they're very, very powerful. Now what you can do is you can take any of these extensions you build and you can plug them in to PowerBatch. Now, if you don't use PowerBatch, I think all of our people who've been using PowerLog a long time are giant PowerBatch fans. Because in PowerBatch, you can string together your screens and your modules, and you can build a processor. So this goes in and it computes a bulk volume, a density, a clay volume, a quick look, a Shaly sand analysis, elastic property calculator, and then it generates a log plot for all the wells in the group, and it prints the log plot. So here's an automated way, and this was a question we had from one of the users, and we've addressed it. And you can create the PDF files, and this is what the PDF file looks like. I want to note that this was a suggestion we added a couple years ago, where the clients wanted to move the curve headers to where they weren't separated; they were showing on top and on bottom. And we also added a track header for easy identification of the tracks. And here's your elastic properties. And then here is your Shaly sand analysis. And here's your quick look analysis. So we did a full interpretation and elastic property calculators in the PowerBatch. And here's the same workflow using the newer Workflow Manager. And you build the same workflow. You calculate the density, porosity, the clay volume, run a quick look, run a Shaly sand analysis, compute the elastic properties, and view the log plot. And this one doesn't print them automatically. Rather, it pops up log plot so you can view the results. Here's your elastic properties. You can see that this lower zone is probably going to be the easier zone to frac. And indeed, that is the pay zone, and that is the zone that the clients are fracking in these wells. And that's an example of that. And let me make some observations that PowerLog continues to be easy to use for geoscientists and engineers. The new functionality is designed to shorten time in data preparation. We're really trying to minimize the amount of time you need to spend normalizing, editing, and patching, so that you can spend more time interpreting. Automation is becoming a lot more common in petrophysics. Python is becoming ubiquitous. In the case of PowerLog, user suggestions drive our development. And we're working on new functionality, and we hope to have it out fairly soon. We'll have an entire automated log interpretation workflow. And once we have that out, we'll send that out to the customers for evaluation, suggestions for improvement. So thank you. And if you have any questions or comments, I can be contacted at fred.jensen@geosoftware.tech. And now I'm going to end the show, and because I still have, I think, a couple of minutes, I want to show one more thing real quickly. This is the new extension we're putting into PowerLog 11.1. It's a multi-well histogram. I'm showing one well here, but if I highlight all the wells, it will go. And this is our Cotton Valley project again. And I'm going to generate a multi-well histogram. My reservoir color, that's the rock that I think is reservoir rock, will be green. The non-reservoir will be red. We're going to use the pay flag to separate them. And we're going to look at the density curve. And I run this. And this is an example of an extension and a viewer. And we're running it over the working interval. It's going to go in process. And so here are the 6 wells. And you now have a multi-well colored histogram where green is the pay section and red is the bulk density of the non-pay section. Now, if you're interested in obtaining this histogram, we will be putting it with the distribution for PowerLog 11.1, or you can email me and I will send it to you, and you can easily add it to your Python extensions and can be running it almost immediately. And with that, I think I'm finished or ready for some questions.
Yeah, we can wrap it up for some questions. We have
a couple of minutes.
So. Yeah. So if anyone does have a question, you can enter into the chat or you can raise your hand and I can open up your mic and your video if you would like. There's a question in the chat.
Your question?
So Fred, do you see the question for you, Fred? In the chat it says,
let me go look in the chat.
I can read it too if you'd like.
Using a discriminator in the synthetic curve generator window would be the same effect as using the sampling grid of your null curve. No, actually it's not. And the reason it's not is because the discriminator does not eliminate the depth. So when you use a discriminator, I don't believe that will eliminate the null curve. Let me think about that for a second. I guess you could try that, but I don't think it will work as well as nulling out the depth samples, and it's quicker than nulling out the depth samples. So let me think about that. So you're saying in synthetic curve generator, and here's the same as OD null, do a model information and curve editing. And you can say you could put in some discriminators here and you could do the same thing. I've never used discriminators in synthetic curve generation, and I'll get back to you. What if someone doesn't know anything about Python programming? Can they still use the Python ecosystem? Yes, it is quite easy to use. It's not a problem. All the extensions, you don't need to know any Python, and we've written the Jupyter workflows, and so you don't need to know Python to use the Jupyter workflows. It's very easy to use. And now Andres Christian said that it is the same. Using discriminators would be the same effect as using the sampling grid of your null curves. And that may be true. I need to go in and look at that. I haven't tested that, but I know it's easier to use the sampling grid of the null curve. And it can be more sophisticated in how you pick that sampling grid using the null curve. In workflow managers with extensions, is trend also used to define properties? You can define a trend curve and use that to define properties, but in the workflow manager, That would have to be, you would add a trend curve selection or a trend curve computation to the workflow manager. So let me bring up workflow manager and file, recall screen, and project. And here's our workflow manager. And then if you wanted to add a trend computation, you could simply add a trend computation in here. And then you could do the same thing. I can get back with you on that one. We'll record your questions and we'll get back to you with more detailed answers in the future. And at that point, I think I'm through with my time.